Today's seminar is going to be given by Jordi Zamora-Munt, who, as you know, has been with us as a postdoc for about a year and a half now. So, Jordi, please.
Thank you very much, Pera. Welcome, everybody. Today, I will talk about extreme events in semiconductor lasers and coupled electronic circuits. I will try to show you some results we have obtained last month in this topic, where we are trying to predict and control, if it's possible, these extreme events in these devices. This is a work that I've been doing in collaboration with several people in different places. Cristina at UPC in Terrassa, and also with Bruno Garvin, Stefan Barlan, and Massimo Giudici at ENLN in Nice, where the experimental part of this work has been done. Also in collaboration with Jorge Predice, now at Nouvelle Calédonie, and with José Ríos Leite in Recife, José Reynoso in Madrid, and also Claudio Miraso and Raúl Toral here at IFISC. This is the outline of my talk. I will introduce the topic of extreme events and also rogue waves and optical rogue waves to show you that some of these extreme events can be deterministic, and we have observed this in semiconductor lasers with continuous wave optical injection. I will show you some results in this topic about the origin and predictability of these optical rogue waves. Then I will show some consistent results with the previous case in about extreme pulses in external cavity semiconductor lasers. And then in a different kind of extreme events, I will show you a method to predict and suppress this kind of particular kind of extreme events known as driving kings in electronic oscillators, and I will conclude. Well, first, as all of you probably had an intuitive idea when I tell you that I will talk about extreme events, this is a very broad topic, is a rather general idea that can be found in different fields. Extreme events are can be observed in different fields, as I mentioned. For example, when we talk about meteorology, large hurricanes that can have potential destructive effects, is what we want to find a way to predict them or prevent this kind of extreme events. Also in other fields, for example, in neurology for epilepsy seizure, you know that neurons fire in different parts of the brain, and in the epilepsy seizure, most of these neurons spike at the same time, and this spiking of large number of neurons can also be considered extreme events. Also, in complex networks, maybe not as obvious as in other cases, there are some nodes in scale-free networks that are much more connected than the others, known as the hubs, that gives an important effect in the evolution or the dynamics behind this kind of networks. Also in stock markets, especially in very speculative stock markets, bubbles and the successive crashes produce large losers in money. That is are events that are also suitable to be predicted, or at least or somehow controlled, in order to avoid this kind of large deviations. And extreme events can also be observed in the ocean. When we look at the waves in the ocean, some of these waves can be very large, much larger than the others, known as rogue waves. I will talk in more detail later. And these large waves can be a risk for the boats or offshore platforms, for example. This is a general idea about in which fields and what can be considered an extreme event. To give you more precise idea of what we consider for an extreme event, we will consider extreme events that are at the tail of L-shaped distributions. These events can be found and are characteristic of these L-shaped distributions and fall outside and far from the average. For example, if you take a look here, you can recognize a Gaussian distribution, a distribution of, for example, random independent events when you measure the height of the several people. And there is a very small probability to find an event that is much more larger in this tail of the Gaussian distribution. However, there are some some probability distributions that has these thick tails, for example, the power law distributions, but this is not exclusive for power laws. Any kind of distributions having a thick tail can be studied in this field of extreme events, just because they have a non-negligible probability of these very large events. There are different ways to quantify this, what is an extreme event and what is not. Here I'm showing just two examples. For example, in the case of rainfalls, one can consider a time interval with different events that happen during this time interval and take the largest event inside this time interval. For example, the largest rainfall in 1 year or 2 years. We can also consider a definition using a threshold. We properly define an extreme event when it is bigger than a given threshold. In both cases, there is some degree of, well, are somehow arbitrary. There is some degree of arbitrariness, but we will consider in our case mostly the definition using a threshold above which we will define an extreme event. A particular type of extreme event are the rogue waves. Rogue waves were introduced in oceanography, and you can see here a handmade sequence of pictures of what is reported when a boat finds one of these rogue waves in the ocean. They appear like wall of waters and appear from nowhere. They are considered almost unpredictable, at least. And they occur in relatively calm, deep oceans. These rogue waves are a risk And it's not strange that some of these rogue waves hit a boat or offshore platforms, for example, causing damages in the ships. So these kind of extreme events have to be taken into account for the design of offshore oil and gas platforms or wind farms, but they have also been identified in other fields and recognized as rogue waves. For example, in acoustics, plasma physics, or optics, and is in this field of optics where I will explain our results. Optical rogue waves were first introduced in 2007 by Soli and co-workers in the generation of supercontinuum in a nonlinear fiber. When detecting the amplitude of the pulses in the output of this nonlinear fiber, most of the pulses have a small amplitude. But from time to time, some of these pulses show much larger amplitudes than the others. The probability distribution of these pulses show this characteristic L shape, and here in the tail of this distribution we can recognize these larger events that can be considered optical rogue waves. This is a very active field, and optical rogue waves have been observed in different devices. For example, continuous wave pumped semi-continuum, also in titanium sapphire lasers, multi-stable systems, Raman fiber lasers, and only this last year you can find around 25 related publications in this topic of optical rogue waves. Most of these publications, most of these optical rogue waves are considered well, stochasticity is considered a necessary ingredient in most of these studies. However, it was shown, and this is the second point of my talk, that in continuous wave optical injected semiconductor lasers, large intensity pulses can also be observed. Here, for example, look at this time trace where there are small oscillations, chaotic oscillations, and from time to time a large pulse is emitted by this device. If we plot the probability distribution of these pulses, we can recognize that some of these events are more frequent than what could be expected from a Gaussian distribution. Interestingly, this behavior can be reproduced with a completely deterministic model, which means a model without any source of stochasticity or random noise, and is shown here that the small amplitude chaotic oscillations that corresponds to the main part of the dynamics show from time to time large intensity pulses.
Yeah, I'm a little bit confused because, I mean, by definition, you always have a stream event, right? Because basically you say something that occurs with a probability less than 1% is a stream event, right? This seems to be the case with the previous transparency. So a rogue wave, with respect to optics, is what is something that is above that. So basically, I mean, you don't have anything specific about the dynamics. It's anything that happens, I mean, with low probability. And looking at the simulation on the right-hand side, it doesn't look that something is happening, right? I mean, it's really decaying exponentially, so nothing special happens beyond data. Well, in the other case, yeah, you could say that it's statistically different. So I'm confused about it.
There are several things to be considered. in case of rogue waves, they must appear in far from the average of the probability distribution. It's also considered, I mean, it's something that I will try to show, that is, well, rogue waves are usually considered unpredictable. I will try to show that deterministic optical rogue waves can be predicted sometime in advance, but is a general concept, and there is no strict definition where everybody agrees in this definition of what is a rogue wave. So, considering that these events happen more frequently than one could expect from a Gaussian distribution, is a starting point to recognize a rogue wave. At least, well, there is something else, of course, that difference between extreme event and rogue wave is this wave then you have to take into account that here you have waves, and some of these waves are much larger than the rest.
Yeah. As far as I recall, in the works like John Dudley did, they really were considering similar mechanisms that lead to the steepening of waves, like in sea waves, leading to these high waves. What would be the corresponding mechanism here? So why this being a rogue wave as opposed to just a high intensity pulse?
Well, because, and I somehow I try to show you, is that if we consider the amplitudes of these oscillations, or the height of these oscillations, some of these amplitudes are much larger than the average.
But it might be a very different mechanism.
Yeah, the mechanism could be different. Actually, in the paper that I showed before, the mechanism is very different from one paper to the other, and and there is probably no a common mechanism for all the optical rogue waves, at least. Well. So, well, considering that a quantitative definition using this threshold criteria I mentioned before, we consider that rogue wave, deterministic optical rogue wave, has a height larger than the average plus 8 times the standard deviation of the heights, here shown in this with these vertical lines. So we consider rogue waves all these events that fall above this threshold. Okay. This work left several questions to be addressed. For example, the mechanisms behind the appearance of these optical rogue waves, but also if they can be predicted or controlled somehow. The experimental setup used to show these large intensity pulses is an external grating tunable semiconductor laser with a fixed frequency, unidirectionally injecting into a single mode VCSEL, where the frequency is varied by tuning the pump current that also changes the frequency due to Joule effect, and properly recorded the output from the slave laser. The dynamics of this slave laser can be well reproduced with two rate equations, one for the slow envelope of the complex electric field, and another for the carrier density. And this model has three main parts. One part for the solitary laser that is characterized by the field decay rate, the line replenishment factor, the carrier decay rate, and the pump current. A second part with one term for the injection strength and another for the frequency detuning. From the slave laser respect the master laser, and we also consider it in part of our work the effect of spontaneous emission noise, while I will show some results without noise.
In injector you only consider the field amplitude or including phase complex number?
Well, yeah, here in the model, you mean?
Yeah.
Yeah, it considers an arbitrary phase equal 0 in this case. Okay.
Is the delta?
Well, but it's
There is the tuning, the oxygen phase is changing all the time.
by using typical parameters for this type of lasers, both the experiment and the model show four main dynamical regimes. Here I show the optical spectra with the intensity in the color code as a function of the pump current. For low pump currents, the slave laser is almost independent from the master laser. By increasing the pump current, we enter in the stable locking regime, where the slave oscillates at the frequency of the master, and then after a sequence of period doubling bifurcations, we enter in a chaotic region, and by further increasing the pump current, we then go again to this beating where both signals are almost independent. And it's inside this chaotic region where the deterministic roadways can be found. This chaotic region depends in a complex way with the pump current and the frequency detuning. Here you can see the maximum Lyapunov exponent with positive values here in yellow and red, showing the chaotic regions depending on these parameters. If we calculate the number of roadways in this parameter space, what we can see is that not in all the regions, in all the chaotic regions, we can see roadways. For example, it's clear here that we have some regions with chaos but without roadways. So our question was why there are chaotic regions with roadways and others without. The first thing we can do is to show the bifurcation diagram by changing the frequency detuning, more or less around here. And here I show the height of the oscillations, and in the color code the events at the given height by changing the frequency detuning between the two lasers. So here we can see the region of frequency locking, the sequence of bifurcations, after which a region of a small chaotic amplitude oscillations can be observed. At some point, at the given frequency detuning, a sudden expansion of the attractor occurs, reaching much larger amplitudes, these oscillations. If we overlap this picture, the threshold, according to the definition I gave you, to define what is a roadway, here this red line, we can see that some of these events are much larger, are above this threshold. That is something that can also be observed in the experiments. these rock waves have something very interesting, interesting property, that is, if we take a long time trace and then take snapshots of 10 nanoseconds of each of these large events and center all these snapshots at the maximum of the peak of these rock waves, we can see that all the trajectories that are more or less independent, shown by this average value, converge to a narrow channel that is actually a precursor of this rock wave. So it gives the chance to identify, if we are able to identify this precursor in the dynamics, it gives us a chance to predict the appearance of these rock waves. That is also observed in the experiments. So our question was, where does it come from? What's the mechanism behind this narrow channel? So, well, before answering this question, what I want to show you is the effect of noise on these dynamics. What happens if we include some noise, actually a strong noise in the dynamics? What we can see is that the precursor still exists, but the number of rock waves is much smaller. For 2 times the length of the time trace, we have a reduction of 1 order of magnitude on the number of these rock waves. With the distribution of inter-rock waves intervals that is in agreement with the experiments. So now our question was, why does it occur? Why we can see this narrow channel? So to better understand this, we can take a look at the phase space of the model. Here I'm showing the real and imaginary parts of the electric field and the carrier density. Our model has 3 fixed points that are shown here: S1, S2, and S3. And S2 is one of the main characters of the appearance of this precursor, because it has an attractive manifold, here showing these blue dots, and a repulsive to the surface. Okay. During the regular part of the trajectory, here, for example, this black interval, the trajectory takes place in a small region of this phase space. But when this rock wave occurs, what happens is that it follows the attractive manifold of S2 for a while, and then is repelled in the direction of this repulsive manifold of S2, and then the rock wave is triggered with a maximum somehow around here. So with this, we have an answer of why this convergence of trajectories before the rock wave happens, but we also want to know why there is a sudden expansion of this chaotic attractor, and why rock waves are observed after this expansion and not before. What we can do is to take a surface, for example at n equal 1, and calculate the crossing points of the trajectories in this surface, something that is called the Poincaré section. Here, this black dots corresponds to the chaotic attractor, and this blue cross is the attractive manifold of S2. So you can see that they are well separated. This corresponds to parameters before the sudden expansion. And they are actually separated by a surface that crosses this Poincaré section in this red region. This is the attractive surface of a saddle point, of the saddle point S1. After this expansion, the attractor crosses this barrier, and some of the trajectories can reach the attractive manifold of S2. What explains why we saw rock waves before after the sudden expansion and not before. Well, our guess was that this structure of a chaotic attractor, a barrier, and a saddle was something general enough or usual enough to find such extreme events in other systems. What we considered is the case of extreme pulses in external cavity semiconductor lasers. An external cavity can be created by injecting the light of a semiconductor laser, for example, reflected in a mirror and reinjected again inside the semiconductor laser. What creates an external cavity, and this system can be modeled by a very similar model, similar to the previous one, just by substituting the continuous wave injection by a feedback term where theta is the feedback delay time, and this corresponds to the coupling strength that will be our control parameter. In this kind of systems, when the time delay is smaller than the period of the relaxation oscillations, we can see a rich variety of dynamics. For example, periodic dynamics, chaos, different regular dynamics known as regular pulse packages, other chaotic dynamics, and is in this sequence of bifurcations where we recognize some events that are extreme and without a clear maximum. So here we also show, we show the bifurcation diagram by increasing the coupling strength, and the red line corresponds to the threshold above which we consider an extreme event. By decreasing the feedback rate, this theta I mentioned, we can see that there is a region where these large amplitude oscillations coexist with other attractors, but not in the first sudden expansion of the attractor. This expansion occurs when the small amplitude chaotic attractor corresponding to these oscillations change intermittently from the system change intermittently from this the dynamic in this chaotic attractor and a larger chaotic attractor, and is in this large amplitude chaotic oscillations where some of these events are much larger than the others. So we suggest this an intermittency between a small and a large amplitude chaotic attractor as a route to extreme events. What was nice to verify is that some of the events observed in the case of continuous wave injection can also be shown by this device. For example, the existence of this precursor that can be clearly observed when we plot in the phase space of the phase difference and the carrier number, where all the trajectories with large intensity pulses converge to this narrow channel. the similarity with what I showed before is more clear if we show the phase space in terms of the intensity and the carrier number, where we can plot the attractive manifold of laser fixed point that is somewhere there, up there, and all the trajectories converge to this attractive manifold, and then are repelled, and a large intensity pulse is triggered. So the results are consistent with what we found for the case of continuous wave injected semiconductor laser. Then what we thought is to find.
To previous transparency, I mean, looking at that, I mean, it comes to my mind an excitable medium, right? So you are doing like that, and suddenly you have a jump. So with your definition, that would be every time you are doing a trajectory, right, to escape from the.
Yeah,
this is a kind of log wave, right? So this is.
We had a lot of discussions about this, but the first thing I should say is that here there is no noise, so it is internal to the chaotic dynamics, these large excursions. The second thing is that this excitability is well defined or previously defined in the case of fixed points or periodic oscillations, but here is less clear what happened with the case of chaos, with chaotic dynamics that do this kind of intermittent trajectories. Maybe I think that could be some similar definition to the usual excitability for the case of chaos, but I think there is no reason to do not think about the possibility of these induced excursions outside the main attractor. So we thought in the possibility to predict the extreme events in a different way, from a different approach. Actually, using anticipated synchronization to predict these events. So for this, we found a paper in arXiv, a very nice paper, dealing with extreme events known as Dragon Kings in coupled electronic oscillators. So they showed that in these chaotic oscillators, electronic chaotic oscillators, unidirectionally coupled in this master-slave configuration, synchronization can occur, complete synchronization, if both circuits are completely identical. They could oscillate in the same way. However, due to parameter mismatch and noise, bubbling can be observed in these systems. These bubbling are small excursions outside the synchronization manifold that can be shown, for example, if we calculate the distance in the phase space between the variables of the master and the slave systems, V1 for the master, for the slave, and so on. Then this distance perpendicular to the synchronization manifold show excursions outside this synchronization manifold that most of them are small, but from time to time large excursions can be observed in this system. Outside the manifold follow a nice power law. However, the largest desynchronization events are much more frequent of what one could expect from the extrapolation of this power law. That is something, well, that is that are events that Didier Sornet coined the term dragon kings, referring for dragon to different species of events, because it suggests a different mechanism for these large events, and king because they correspond to the end of the tail of the probability distribution. They suggested a way to control these dragon kings by using a threshold in one of the variables. What we did is to suggest a different mechanism with this anticipated synchronization. Anticipated synchronization can be achieved by properly coupling two systems with a negative feedback loop. Okay, in this way, where X corresponds to the main system and Y corresponds to the auxiliary system. If the dynamics of the auxiliary system is equal to the dynamics of the main system a time tau in advance, the time tau corresponding to the feedback delay loop, then this solution is stable and the dynamics of Y is equal to the dynamics of X, but anticipated at time tau. By applying this coupling mechanism, we can reproduce with the auxiliary system the dynamics of the main system here in black and the auxiliary in red, but the dynamics of the auxiliary system is anticipated at delay time tau with respect to the dynamics of the main system. So it gives some anticipation time to react and try to prevent the appearance of these dragon kings that corresponds to these large desynchronization events. How can we control this? Which is the method we can apply? For example, in our case, we considered corrective reset of one of the variables of the system. For this, at a given threshold, when this variable perpendicular x crosses a given threshold, we apply this reset of the variables of for one of the variables of the slave, which means that when the trajectory of the master and the trajectory of the slave becomes different, we try to bring together again the trajectory of the slave to the trajectory of the master. Okay, for weak resets, if we apply this reset directly, well, considering a threshold in the main system, this is the reset we apply. We can see that this reset sometimes is not large enough, and the difference between the master and the slave of the main system continues growing, and then one of these large desynchronization events, these dragon kings, are observed. However, if we consider the same weak reset in the auxiliary system, we see that we can control, actually suppress all these dragon kings efficiently. Okay, here shown when these corrective resets are applied. So what we showed is that this method, using anticipated synchronization, is more efficient than applying directly the corrective reset by checking the threshold in the main system. That is something that you can see, for example, here, where I'm showing the number of roundings over when we apply a given control reset BC over the number of roundings without any control. So at different thresholds, we can see different behaviors, and the solid lines corresponds to the case of checking the threshold in the anticipated system, and the dashed lines checking the threshold in the main system. What we can see is that a complete suppression occurs before for smaller control resets when we check the anticipated variable, and is something that we can see in both in the case of the synchronization events induced by parameter mismatch, a completely deterministic induced event, but also if we consider identical parameters for both, well, for all the oscillators, and we introduce a source of noise that induces this bubbling, where we also observe a reduction of the controlling of control voltage from one respect to the other. So, in conclusion, extreme events can be found in many complex systems due to this general definition of what is an extreme event, and they are of particular interest due to their potential destructive effects. Continuous wave optical injected semiconductor lasers can show these irregular and infrequent extreme intensity pulses that has been identified as deterministic optical rogue waves. We showed that they can be predicted with some anticipation that gives us a hope to avoid the possible destructive effects. Noise substantially reduces the number of rogue waves, but also anticipates the bifurcation. It's something I didn't show, but we also studied that noise before the sudden expansion can trigger some of these excursions, something maybe related with excitability, Victor said before. An external crisis-like bifurcation enables access to the region in the phase space where rogue waves can be triggered, showing this structure of chaotic attractor, barrier, and saddle. In semiconductor lasers with optical feedback, in the short cavity regime, a consistent behavior was observed, and we suggest intermittency between these two small and large amplitude attractors as a route to extreme pulses, and extreme desynchronization events can be efficiently predicted and suppressed using anticipated synchronization and reset pulses. Thank you very much.
Thank you, Jordi. Questions?
Jordi, what means external crisis-like? What's the difference to the external crisis?
Well, yeah, we had a lot of discussions about this, because and the name comes from the fact that we couldn't find in the literature a proper definition that matched what we were seeing here. The name of external crisis-like means that the chaotic attractor that appears from one of the fixed points collides with the attractive manifold from a different fixed point. Okay, this is different from, for example, the exterior crisis, where the
boundary crisis, you mean?
Or yeah, boundary crisis. Sorry, where the collision is between the manifold of one of the fixed points and the attractor created in the same fixed point. There are many possibilities, a lot of different crises. A way to fit what we were observing here with the things we observed in the described in the
Hello? I'd like to ask you something a little bit maybe provocative. In your opinion, conceptually, what is new in the I mean, what justifies all this that you mentioned there are 25 papers in 2013 about just optical rock waves. What justifies all this strong interest in this phenomenon? Because you were mentioning that one of your mechanisms are crises, and crises were suggested in '83, and so the fact that you're at one side of the crisis, and if you, I mean, with your definition, you do the average and then take how many segments. So, I mean, these were okay for sure. Also was mentioned in a question by Victor about excitability. I mean, with Damian Pera, we suggested that we made a study on excitability mediated by a homoclinic bifurcation. If you are, I mean, very close to the bifurcation on one side, and you're in the fixed point, so it's you make the average and so on. But then you may have this strong jump. Or for instance, with Emilio and Pera, we made a report for a European project, and always that you have as a critical bifurcation. If you are close, you can jump, I mean, very, very far. So there's a second part in the talk that is the control and so on. And I really think this is new. I mean, because there was no this emphasis. But in the rock waves themselves, I mean, what do you think?
Well, in my opinion, is what is really new is the detail of these studies and the statistics that has been done in all these extreme events. There is also an increasing interest, for example, in the field of solitons. That is something that was not done before, where these solitons has a shape or characteristic similar to these rock waves, so they can be used to have a better understanding of what is happening in the ocean. I think it's basically this relation between different fields that were initially just for oceanography or just for optics. Maybe you...
What binds this together? The mechanisms are completely different.
For example?
The definition is too elastic, I think.
Yeah.
Yeah.
No, but you are, yeah, of course, you are not saying that the mechanism for one of these things. Well, wait. For example, in the case of rock waves, for the solitons, you can use the nonlinear Schrödinger equation that is also used to model the waves in the ocean. So, for example, here is
but I think, I'm sure you have discussed this several times, but I don't like calling the optical rock waves you have explained as rock waves, because my English is not really good, but a rock man is someone that wanders around, it's a solitary man that is thinking how to make something bad to the others, and then when it goes to find some other, then makes a bad thing. This is a rock man. And then the idea of rock waves was like this, was solitary waves going around in the sea, and when they find some ship, this was the idea, if I understand properly. And I think that the what is called rock waves in the semiconductor basis is completely different, because the models is different when you look at rock waves on fibers. This is different. But in semiconductor lasers, we are working always with the slowly varying amplitude of the electric field. It means that what has the big amplitude is not one crest of one wave, which is what happens in hydrodynamics, but it's millions of crests of the wave, of the optical wave, which is on the envelope. So it's the coherent motion of one army of rock elements going up and down. I think this is completely different from the proposition hydrodynamics. You can call it the same or different, but I think that the idea of rock, of being something isolated, doing something bad, is completely loose. Really lost in the semiconductor laser application. I don't like calling these rock waves.
Yeah, well, yeah, it's a criticism. I agree with you that there are differences between the rock waves, the optical rock waves, for example, in the case of solitons. But we are here also considering waves that are in the same way propagating through the medium and then through
this
the
is
air.
what I don't agree. It's propagating, it's bouncing back inside the laser. It's different when you have a fiber in which things is propagating. I agree calling rock waves there, but in the semiconductor lasers you don't have you have bouncing waves in the resonator, which is quite different, I guess. Well, it's just a nomenclature, but it refers that there are many different mechanisms, and because the mechanisms are very far from the original name.
Yeah, and
maybe in that context as well, nomenclature. Would you call mode lock pulses in the laser dragon things? That would show the same statistics.
So like an explanation. More often than explanation.
Yeah, sure.
Then the younger
yeah, no, you said dragon
Mode pulses in the laser. Would the mode lock pulses be dragon things?
Well, the definition of dragon kings, as far as I know, corresponds to these events that play at the end. So initially it's open to, it's not related with a precise.
It's not related with the mechanism.
With the mechanism.
It's just related to the statistics.
As far as.
Yeah, you have two systems which are oscillators, which are detuned, which are coupled, and one coupled to the other. From time to time, the wave system synchronizes the pulse on the one, on the master. No? And that's similar to a mode laser. Of course, we can invent a new name every time, but so
that would be nice.
Well, I guess the point here is about the statistics, is it? So the way that this one. So the question is, you have here this. So it's chaotic attractor, and from time to time you reach the channel, and then you make this distortion, and then go back to the attractor, and then something like that. So the point is that here you go to that place with a certain interval that does not follow an exponential, but is something like an exponential. So do you know any reason for that? So is there any reason for that, or just any chaotic attractor would do that, or is it not this case? Or?
Well.
So my question is, you have a chaotic attractor. You have to reach the channel.
Yeah.
The point is, given a chaotic attraction, a chaotic attractor, how often do you go to that region in phase space? With which distribution does that follow?
Well, for example, for the continuous wave injected laser, it follows an exponential distribution, the time between consecutive large intensity pulses. Okay. That is something that is also observed for this for other sudden expansions of the attractor. This we have not calculated analytically the mean passage time outside the main attractor.
There is no known result about which is the passage time for a given chaotic attractor to go to the same place.
Not in our case, as far as I know.
I have a more naive question. So can I have something to do?
We don't have. Can you show the picture of the events obtained in the by John Dudley on the or the ones in the optics? Yeah, here. Here basically you have these very large peaks and then quiet, and there is very few peaks on intermediate size. And the same happens in this dragon king thing, that there is a maximum of the probability. But your definition, you just show a long tail distribution. So my question is, it is the same that you have a distribution that is going monotonously down and it's just long tail to the fact that you have a distribution that has a second maximum? Is qualitatively everything the same?
They are both extreme events.
Yeah, but one has a probability distribution which is like that.
It's
the
like
other has a probability distribution which is like that.
Mhm.
So my question is, it is qualitatively everything the same?
The mechanism behind
To me it's not. Because this is the minimum and I can define it clearly.
It was intended as
I showed this 1/x function just to give you an idea about what I mean by L shape, but it's not necessary to have a monotonous decrease of the.
But my question is not if it is necessary to have an L. My question is if it is necessary to have a maximum here. Because now here you have a characteristic size where you can divide events. And in the other case, you don't have any characteristic size where you decide what is big.
Are different things, yeah.
Why 8 times sigma? Why not 9? Why not 10? Why not 7? It's arbitrary. 8
Right.
is as nice number as 7.
It is.
Well, 7 is nicer. Yeah, it's prime, I mean, you know.
But the point.
So my point is that in the dragons and for in order you have this, and then of course you can say, well, there is two kinds of events: small and big.
And the mechanism can be different.
Right, but when you have a continuous tail, which is smoothly and monotonously going down, it's not the same. And I don't see the distinction.
Can the mechanism for the periods of the largest one, you mean, can be the same in the case, for example, of power laws?
Yeah, why not?
Yeah, I agree. But
So in all these studies, there is no distinction of all that.
no, because we are considering just the largest events of the distribution, independently of the mechanisms, for example, what happened.
not use the studies is the second case. You have the maximum, you have this frontier, you have this.
No, that was for the electrical
I
circuit,
think-
but not for the laser. It's not that way.
Well, the winter was it? Because
No.
you have
The
this.
laser, for example, is just a distribution that
You have the matrix for dispersion and so
is
on.
of this shape in a logarithmic scale, let's say. Something that could be identified more or less as a Gaussian at the beginning, and then events that are much more frequent and enlarge the tail of these probabilities.
Okay. Any other question?
I was a bit confused by this part where the extreme events you consider by the bubbling rate, right? So you distinguish between deterministic ones due to parameter mismatch and the stochastically induced ones. I'm not sure, I mean, you're using the auxiliary system approach, but how are you going to predict noise-induced desynchronization in one system? I mean, first you have the channel to the auxiliary system.
You mean why the noise that is generating this desynchronization?
I mean, in a deterministic case, you have the desynchronization against the bubbling because of the shape of the attractors.
Yeah.
But in the noise-induced ones, not so much. So why would that work anyway?
Well, my point is here that after you perturb the system outside the synchronization manifold, there is a deterministic excursion that brings back the system again to the synchronization manifold. So here you are predicting when this deterministic part of the excursion starts, after this stochastic process perturbs the system from the synchronization manifold.
Wait, so basically you predict the desynchronization after it happens, so to speak, because by the excursion dynamics or reinjection into the synchronization manifold or whatever you want to call it, by that you make a statement about the point of origin and phase space of desynchronization, basically? I mean, that's what you need to predict the point in time.
Well, I'm not predicting, of course, the stochastic dynamics behind all of this. But these stochastic dynamics perturb the system in a way that these excursions are somehow deterministic. And this is what can be predicted. The evolution after this perturbation occurs.
More questions? If not, we'll stop here. Thanks to the Bueno, que seguimos, cada que seguimos,